Welcome. If you're getting ready for your Unit 4 exam on advanced water treatment, then you are in exactly the right place. We are going to break down all the core processes that you absolutely need to master. Okay, let's get into it. So here's our game plan. We're going to cover 6 key areas. We'll start with those dissolved ions, then move on to specific troublemakers like iron and fluoride. By the time we're done, you're going to have a really solid handle on all these advanced treatment processes for your exam. All right, first up, ion exchange. The best way to think about this is the power of the swap. It's a really fundamental process for removing dissolved minerals. You'll also see it called demineralization. And it's all about targeting those invisible ionic contaminants. Now, the key thing to lock in here is that we are targeting ions. Those little charged particles from dissolved salts. The goal here isn't just softening the water. It's about getting an incredibly high level of purity. Think something similar to distilled water, but frankly, at a much lower cost. So, how does this actually work? Well, it's a simple but really powerful swap. Inside the column, you have these things called resin beads, and they're coated with specific ions. As the contaminated water flows through, the resin has a stronger attraction, a higher affinity for the unwanted ions in the water than for the ones it's currently holding. So it literally just grabs the contaminants and releases its own ions. Now, for total demineralization, and this is the cool part, we use resins that swap out contaminant cations for hydrogen ions, H+, and anions for hydroxyl ions, OH-. So what do you get when H+ and OH- combine? You got it. Pure H2O. Okay, for your exam, you definitely need to understand the trade-off here. Two-bed systems are kind of the workhorses. You have one tank with cation resin, a second tank with anion resin. They work great, they're simpler to regenerate, but they can have something called sodium leakage. Mixed-bed systems, on the other hand, jam both resins into one single tank. This gives you ultra-pure water, because the exchange happens all at once. But believe me, regeneration is way more complex, and the system is a lot more sensitive to getting fouled up. This is your cheat sheet for the different tools in the ion exchange toolbox. For full demineralization, the power couple is a strong acid cation, or SAC resin, followed by a strong base anion, or SBA resin. The SAC grabs all the cations and kicks out hydrogen ions, and then the SBA grabs all the anions and kicks out hydroxide ions. The weak acid and weak base resins, they're more like specialized tools, often used for things like dealkalization. They're really well known for their high regeneration efficiency. All right, next up is adsorption, and please be careful with the spelling here. This is not absorption, where something soaks in like a sponge. No, this is adsorption, and it's all about what happens on the surface. So the magic ingredient here is an adsorbent material that has a ridiculously massive internal surface area. Seriously, think of it like a piece of molecular Velcro. The adsorbent isn't soaking up the contaminants, it's just providing this huge surface for them to get stuck to as the water flows by. And the undisputed champion of adsorption is activated carbon. For your exam, you need to know this stuff is fantastic at removing dissolved organic compounds. It comes in different forms too. Powdered activated carbon, PAC, you can dose that directly into the water. Granular activated carbon, GAC, that gets used in filter beds. But here's the key operational detail. Once the carbon is totally saturated with contaminants, you can recharge it, thermally regenerate it in a super hot oven, and use it all over again. That's absolutely vital for keeping costs down. Okay, now let's switch gears and look at a totally different approach, membranes. So if ion exchange is a chemical swap and adsorption is molecular Velcro, then you can think of membranes as physical barriers. They act like incredibly fine sieves or gatekeepers. Let's look at these as a spectrum where the pores just get tighter and tighter. First up, we have microfiltration. With a pore size down to about 0.1 micrometers, it's really effective at getting rid of bigger particles, any cloudiness in the water, and even bacteria. Now let's step down in size to ultrafiltration. Here, the pores are an order of magnitude smaller. That means they can block everything microfiltration does, plus much, much smaller contaminants, like viruses. Go even tighter, and you've got nanofiltration. We're now talking about the nanometer range, and this membrane is so tight, it can actually start removing dissolved molecules, including those divalent ions that cause water hardness. And finally, we get to the ultimate physical barrier, reverse osmosis, or RO. The pores here are so incredibly tiny that pretty much nothing but water molecules can squeeze through. It rejects almost all dissolved salts and ions. This is the tech behind desalination. So that's the key question, right? It leads us away from pressure-driven filtration to a whole different kind of membrane technology. See, RO uses a ton of pressure to push water through a barrier, but there is another way. Yeah, instead of filtering, electrodialysis uses the power of electricity. You place a positive and a negative electrode in the water, and you stack these alternating cation and anion selective membranes between them. When you flip the switch, the positive cations get pulled toward the negative electrode, and the negative anions get pulled toward the positive one. And those special membranes, they direct all these ions into separate channels, which creates one stream of purified water and another stream of concentrated brine. Okay, let's pivot to two super common problem elements, especially if you're dealing with groundwater: iron and manganese. Now, they're not typically a direct health threat at low levels, but man, do they cause some major aesthetic and operational headaches. And it's not just about how things look, even though those red-orange stains from iron and the black stains from manganese are a huge customer complaint. Operationally, these things react with chlorine, which jacks up your chlorine demand and makes your disinfection less efficient and more expensive. And mechanically, their deposits can build up and clog everything: pipes, meters, valves, and just kill the pressure and efficiency of the whole system. So this table shows your main options, and you'll notice they all share a common theme: oxidation. The main idea is to take the dissolved soluble iron and manganese and oxidize them so they turn into solid, insoluble particles, because then you can just filter them out easily. Aeration uses air, chlorine and ozone use chemical power, and then you have media like manganese green sand that act as a catalyst to speed up the whole reaction right there on the filter itself. Next, we need to tackle a contaminant that's pretty unique, because in small amounts, it's actually beneficial, but when you get too much of it, it's really harmful. Let's talk about fluoride. This right here is the critical balance you have to remember for the exam. At levels around 1 milligram per liter, fluoride is great for preventing cavities. But once those concentrations get too high, it becomes toxic. It starts with dental fluorosis, that's the staining and pitting of the teeth, and it can progress all the way to skeletal fluorosis, which is a crippling disease that actually deforms your bones and joints. It's irreversible, there's no cure, and that is why removing excess fluoride is so incredibly important. This summary shows you a few different options. You've got activated alumina, which uses adsorption, and RO, which just physically blocks the fluoride. But a really key one to remember is the Nalgonda technique. It uses common chemicals like alum and lime to make the fluoride precipitate out of the water. Its simplicity and low cost make it absolutely vital in regions like India, even though its main drawback is the sludge it produces. Okay, so we've covered all the individual tools in our advanced treatment toolkit. Now for the final and honestly most important part of your exam prep: putting it all together. How do you choose the right process, or maybe a combination of processes, for the job? This table right here, this puts the entire unit together on one slide. This is your ultimate study guide. For each of these technologies, you need to know its primary target and its core principle. Ion exchange swaps ions. Adsorption binds organics to a surface. RO uses pressure. Electrodialysis uses electricity. Oxidation changes metals into solids you can filter. If you can explain the what and the how for every single one of these, you are in great shape. And here's the final takeaway. Real-world water problems are almost never simple. They usually require a multi-step treatment train. So think about this exam-style scenario. How would you handle high fluoride, high arsenic, and high hardness all at once? Could one process do it all? Or would you need to string together several of the technologies we've just talked about? Thinking through the why behind your choices, that is exactly what's going to set you up for success. Good luck with your studies.